Hello and welcome to the circle angle discovery review video. So this is for those of you who might have missed the lesson and just want to see what we were talking about in class. And maybe if you were in class and you just weren't sure on a couple things, you can kind of see what we did just to retrace your steps a bit. So while we watch this video, you should have a few things with you. You should have the GeoGebra document, which is going to be the whole exercise that we walked through. All the hands-on stuff is done in GeoGebra, which that has a link in the Weebly website, as well as the classwork if you don't have that already. So what you should do is have a printout of the classwork, so you can look on with the scenarios that I talk about, the GeoGebra document, in case you want to switch back and try some of the stuff I'm doing on your own, and you should have this video, which is going to explain the concepts of everything we went over in class. So the first thing is just to talk about the angle of a full circle and the arc length of a full circle. So right now we're only dealing with degrees. So a full circle is 360 degrees. We know that angle if we started with a center point, the line going this way. If we went all the way around, that's 360 degrees. So we would say this arc length in degrees is also going to be 360 degrees. This 360 degrees is regardless of radius length. It's just going to be the full circumference of the circle. So every circle has an arc length of 360 degrees. Now if we take half of that, that means a semicircle would have an arc length of 180 degrees. This is also the arc length generated by the flat line angle from the diameter. So if we have a diameter, this is going to come up later, if you have a diameter, it creates a 180 degree arc. Now if we cut that in half, this one doesn't come up quite as much, but it is still useful. If you have any kind of right angle with radii, or maybe two diameters, this would give you a 90 degree arc. Now we have types of circle lines. This should be review, something that you know from previous classes. So I'm not going to go into describing the different types of lines, but we can see in this picture already that we have different angles all over the place. So let's just get these line names in there. So we've got radius, arc, chord, diameter, secant, and tangent. Secant and tangent being very, very similar. We'll talk about that later. So the other thing that's in this is that we have different angles. You can see the ones on the inside. We have angle BGA right here. It's kind of a larger angle. We have a very small angle F on the outside made by tangent and secant. So these angles that are made with the different kinds of lines is what this lesson is all about. Okay, so this is what the GeoGebra document looks like. So we have a circle in the middle with an angle labeled here. You can see that we have a red arc highlighted, we have the angle measure, and the arc measures to the left. So we're going to kind of keep track of all these things, how they change as we go through each of the scenarios that come up on the next couple pages. So the first thing you might have noticed is that we talk about angles. The first angle being referenced is this angle theta. There's another angle alpha, which if I move this slider over a little bit, it'll pop up at some point. There it is. It's just going to be the vertical angle to theta. So we have theta, alpha, they are vertical angles and they are equal. So this process is really going to be the same thing on either side. So we're just going to be dealing with this smaller arc AB through the whole process, but this could be the same thing if we were moving this point farther to the left with arc FE being this kind of anchored arc that's not moving too much. So as we move through the examples, we'll see that AB is going to stay pretty much in the same place almost the whole time. And we're moving point P, so we'll see a bigger change with FE. So we'll see FE changing, as you can see right now, where AB is staying the same. So just to kind of play with the slider here to see what's going on, we have this point P that's either moving to the right, and we can move all the way outside the circle, and we can go all the way to the left, which brings F and E almost to point P. So this angle could be anywhere from about 180 degrees, we can see there it's 173, to pretty small. The smallest it gets is 26, but if I made it go way off the screen, it would probably get pretty close to 0. So now to bring it back, the other picture we have is this little bow on the bottom of the screen. So as we go through this, I want you to kind of remember that we're starting in the center. So starting in the center is kind of like starting with a diameter here. And with a bow, if you pull back the arrow of a bow, we can see the string bending. And we get this angle that's smaller. So you can see this green angle on the inside here. All the way to the right, it's about 73 degrees. But where it starts, it's about 180 degrees. So we see that similarity here when I have the slider all the way to the left, it's almost 180. when I move further away. It's like pulling back the string of a bow. So thinking about how that angle gets smaller, the farther back you pull the string, that might help put some context into all the formulas that we talk about as we move throughout the lesson. Alright, so let's take a look at scenario number 1. Scenario number 1, it says to do the directions first and move the slider to 0. So right now it is at 0, so I'm already there. And this is going to be an angle between two diameters. So we have this line here which goes through the center, this line here which goes through the center. So these must be two diameters if we include the blue radius and the dotted radius as the full line, the diameter. So when we have two diameters that intersect, sometimes you might just see it as two radii, we get this central angle. So that's the name for this. This is a central angle. And the reason why it's called a central angle is because the vertex is right in the center of the circle. Now let's look at some of the measurements. We have the angle theta is 90 degrees. Also arc AB is 90 degrees. So this red arc is the same as this blue arc here. And then we also have the arc EF, which would be on the other side of the circle, not currently highlighted, but that one's also 90 degrees. So we could come up with two formulas. One is going to be a simple formula, which is what we're going to use pretty much always, but we could also come up with a formula using all three of these, including the arc EF, that wouldn't be drawn in your picture and is not highlighted here. So it's not highlighted here, but we'll see as we go through, and probably by the end of it I'll cycle through all these earlier examples too, just to show you exactly what this connection is. That it's really the same thing throughout the whole 4 or 5 scenarios that we go through. So this is going to be the central angle where theta is equal to the intercepted arc. So theta is equal to arc AB. So now we can move on to scenario number 2. So if we move on to scenario number 2, what we have is this point being moved over to the edge of the circle. So the edge is right at 3. I just know that because I made it that way. So if I bring this all the way to 3, exactly at 3, now this point is going to be exactly on the edge of a circle. If you remember, something that we've done before right on the edge of a circle is a construction with a triangle or a square with its points inscribed on the circle. That means that it has its points right on the edge. So because this vertex is right on the edge, this is called the inscribed angle. So now this is made by two chords, not diameters anymore, because now they're going to be on either side, not going through the center necessarily. There could be a diameter mix in here, but in this case, so the general example is two chords. And it's going to have an angle measure of 45 degrees where the arc AB is 90 degrees. So AB is 90 degrees, EF is 0, and angle theta is half of it. So again, we have this relationship between just this arc and angle theta, where angle theta is just half that arc. So we can think about this as the equation that theta equals 1/2 of arc AB. However, because we know that AB didn't change, but the angle definitely did, so this arc EF, even though we haven't seen it yet, this arc EF, but the fact that it's 0 now, where it was 90 before, definitely has something to do with this. So we saw before that when they were both 90, this angle was 90. When they're both different, where 90 and 0 makes an angle of 45, it seems that this 45 is kind of right in between these two angles. So let me bring it back. So between situation 1 and scenario 1 we had 90, 90. If this angle was right in between these two values, they would all be 90, so that makes sense. Now if we bring it over to 3, if 45 is right in between these two, that kind of makes sense too. So it's a little interesting here that we see this situation even though this arc EF hasn't popped up yet. Okay, so now we're on to scenario 3, which is just going to be this point here being anywhere in between the edge and C. So definitely take a look at how EF is changing, because we've seen that AB is kind of going to be the same, so it's not particularly interesting. But as we move P to the right or to the left, notice how EF changes. When it's starting close to the center, EF is getting bigger. As it goes farther and farther away, EF gets smaller. So we see this change in EF as we move point P. So now for this situation, your picture could have any one of these illustrations that I'm showing here as the slider moves back and forth. As long as P is on the inside of the circle between C and the edge of the circle. So I'm going to leave it right there just to get a nice picture there. So now what we have is this angle AB, or sorry, arc AB, and we have an arc FE with the theta in between. So now we can see that we have two red arcs. And if you remember, we were thinking maybe this angle might be in between these two measures, so let's think about it. So if we have 26.14 to 90, this is kind of close to 30, this is kind of close to 60, 60 is right in between 30 and 90. So in fact, this is going to give us our third and actually most valuable equation. And that's just the equation of the average. It turns out that if you actually did the math with these numbers, 90 plus 26.14, that's going to be 116.14, and half of 116 is 58, half of 0.14 is 0.07. So this is going to be the average of the arcs. So theta is the average of the arcs. So that is going to be really what we've seen the whole time. Every single time, the angle is the average of the arcs. So we have this angle is 58 degrees, but I'm just going to call it theta equals AB, arc AB, plus arc EF divided by 2. So that's the average formula. Theta equals arc AB plus arc EF all divided by 2. Alright, so now we're on to the final part where we're going to look at the final scenario. There is a fifth scenario in there, but I'm really going to try to emphasize that it's no different from the last one that we have. So now what we have to do is move this point P on the outside. So pay careful attention to EF, which we saw that they get close together. Then they become 0. And now point P is on the outside and it's pink. Not only that, but where we had E on the bottom, now as soon as P is on the outside, E is on the top. So E and F kind of flip. But we can see now this arc is kind of getting bigger. But it is getting bigger in what I'm going to call the pink direction instead of the red direction. So now that it's pink, these are flipped, it's almost like being negative. As we know from the bow example, this angle should be getting smaller and smaller the farther away P moves from AB. So the farther away P moves from AB, this angle should be getting smaller. So even though EF is getting bigger now, this angle continues to shrink. So now let's think about how we can maybe come up with this equation for that, because the average isn't going to work if we think about these as straight distances anymore. But if we think about this inverted distance, right, so these two flipped, this is now negative. So if we think about this as a negative distance, then maybe it's going to be the average of these two with EF being negative. So if we take P and bring it out as far as it'll go, we get 37.63. So now if we subtracted 90 minus 37.63, divided that by 2, you get 26.18. So take a second to try that. So if that worked, then we have this idea. Okay, so now we can just have this idea that if we start here, this is kind of going to be a recap of all the scenarios. So if we start in the center, this is the average of these two arcs, but it's the average of two of the same thing. So it's just going to be the same. So we can just think of this theta as being that arc. If we move it a little bit, it's the average of these two arcs made by the two lines that cut across. So I can just take these two arc lengths, take their average, and that's this angle in the center. Coming to the edge, E and F now is together at a 0 measured arc, and we just have the average of 90 and 0, which is just going to be 90 plus 0, which is 90, divided by 2, which is 45. So now we get this angle theta, which is half the arc AB. And if we move now, E and F have inverted, so now, this is perfect. Now we've got this nice number to work with here. So 90 minus 27, that's going to be 63, divided by 2 is 31.5. So we can see that this subtraction, when they're inverted, when this P is on the outside, it's just like the average, but we're subtracting them now instead of adding them. And it's always going to be the bigger one minus the smaller one. So whenever this point P is on the outside, we subtract EF. Now before we look at any of the equations altogether, there's one thing I really want to drive home, and that's the difference between a secant and a tangent. So here we can see we have two secants. We have AP and BP, which have these arcs EF and AB with some space in between them. So we have this whole thing AE and BF, which we haven't said anything about the entire exercise, but it's what separates the two arcs that we have been using, AB and EF. So I'm going to change this secant line to a tangent line. Now this is actually going to have me change the picture. So I'm going to drag up A, and you can see E is moving towards A until they basically become the same point. So here we are at the point where AE is almost the exact same point right there. So if we had continued this line, this is exactly what a tangent line would look like. So the only difference is that this arc BA, now AE would be the same point, is touching the F. So now these two arcs are just touching. That's the only difference. We don't have, as you can see on the bottom, this space between B and F. It's just the same point. So there's no difference in the equation. We still use subtraction because P is on the outside. So the only difference between a secant and a tangent is that we use the two arcs that are now touching at that tangent point. There's no space in between them as there was with the secant. Now this will totally give you every situation where we have a tangent instead of a secant. So here's all the equations written out. This is on the bottom of the warm-up sheet. But this is really what we're going to use for all the practice questions. So basically, by walking through each scenario, we come up with this idea of an average between the two arcs every time. And you can see that simplifying those equations gives you these below. Now there is a key to every practice question located on the website as well. So if you look on the bottom right-hand side of the screen, you should see on the Weebly website a key to all the practice questions, which we have the work. Just keep in mind as you go through these questions that as long as you can get the formula based on the situation, we could either have a variable for the angle or a variable for one of the arcs. And that should be it. This is pretty much just a lesson on a key to memorizing these formulas. Hopefully this helps. Have a good one.